I will explain about the background, objective, and methods used in this research.
Milk composed of 3.3% protein by weight, 80% are caseins, which are alpha S1 casein, alpha S2 casein, beta casein, and kappa casein. 20% are whey proteins, which are alpha lactalbumin and beta lactoglobulin. For the second one is genetic background, which composed of casein genes, which we can find on chromosome 6, and whey protein genes, which we can find on chromosome 5 and 11. For beta casein and A1 or A2 variants, there are 13 genetic variants of beta casein identified. For the most common one is A1, which has histidine at position 67, and A2 has proline. Protein composition is important to determine the nutritional value of the milk, properties of the milk, and how they play a role in the profitability and quality of the milk.
The aim of the study was to develop a reliable and rapid reverse phase high-performance liquid chromatography (RPHPLC) method. This method was developed to simultaneously determine the separation and quantification of main bovine milk protein fractions, including their genetic variants. The study also focused on validating the method. The method procedure was applied to analyze raw individual, bulk, and commercially available heat-treated cow milk samples.
There are three methods used for this research, such as validation procedure, sample preparation, and denaturation and reduction. For the first method, which is validation procedure, this procedure includes linearity test, reparability assessment, reproducibility determination, and LOD and LOQ calculation. For the second method is sample preparation for RPHPLC analysis. The main bovine milk protein and its genetic variants were prepared and quantified. This analysis was achieved in 20 minutes, which is a lot shorter than previous method. For the last method is denaturation and reduction using specific buffer. Several steps for this method are sample buffer composition, mixing with milk samples, vortexing and incubation, defatting, and dilution of cerebralized sample.
So for the analysis of bovine milk as conducted in this experiment, there will be 4 types of samples to be used for the analysis. The first one is the bulk raw milk sample, which comes directly from cow. Secondly, the bulk pasteurized milk sample. And the third one is the ESL milk sample. ESL means extended sub-type, and that is the type of milk to be stored. And the fourth one, extended individual host clinical milk samples, and we already confirm the data status of each of the present. So the following here outlines the sample preparation process in detail for each bovine milk sample. So firstly, the milk sample is added with the buffer in a 1:1 ratio, and the buffer consists of a mixture of guanidine hydrochloride, 3.1 molar of bistrates, 9.45 molar of millimolar of DDT, 5.37 millimolar of trisodium citrate. So each of the sample is vortexed for 10 seconds, then incubated at 1 hour at 4 degrees at room temperature. Then we proceed to the defattation process by microcentrifugation. It is done in order to remove the fat layer. So once we've already conducted defattation, we will obtain the supernatant. And the supernatant will be diluted 1:4 with solution B, which is 4.5 molar GDN HCl. And in this slide, we can see the flowchart for the sample preparation process as I mentioned earlier. So the chromatographic technique used in this analysis is reverse phase HPLC, which is RPHPLC. It uses a non-polar stationary phase and a polar mobile phase. And this technique will able to separate the proteins based on elution order of decreasing polarity. So it means that the more polar compounds will be eluted first, then the non-polar compounds will be eluted later. So in the RPHPLC setup, for the experiment, we use the HPLC model of Perkin-Elmer-Flexner HPLC system. It uses a stationary phase, which is a non-polar C18 column of 3.6 micrometer particle size, which is set at the column temperature of 40 degrees Celsius and sample vial temperature of 10 degrees Celsius. The injection volume used is 20 microliters, and it uses a detector of diode array detector DAD at a wavelength of 240 nanometers. So, as for the mobile phase, we use 2 types of solvents, which are first the solvent A, which is 0.1% TFA and 10% acetonitrile in ultra pure water, and the second one is solvent B, which is 0.1% TFA in 90% acetonitrile and 10% in ultra pure water. So we can see here that solvent B is more non-polar compared to solvent A. Okay, so we use gradient elution. in which the polarity of mobile phase decreases from, we will use 29.1% B to 54.0% B over 20 minutes. So we use a flow rate of 1.1 milliliters per minute for the experiment.
I'll be going over the results from this study that look into a faster and more efficient way to analyze milk protein using RP-HPLC method. Alright, let's talk about the protein separation and identification. So the RP-HPLC method was able to clearly separate the main milk protein, which is this include two kinds of protein. They are casein and whey protein. So for casein, the main milk protein that can be separated is kappa casein, alpha S1 casein, alpha S2 casein, and beta casein. Meanwhile, for whey protein is alpha lactobumin and beta lactoglobin A and beta lactoglobin B. One of the highlights is that the entire process took just 20 minutes, which is much quicker than other methods. That means that this method gives better efficiency and potentially lower cost. Moving on, let's look into the chromatographic profiles of milk sample. From here, we can observe that the method identifies genetic variant, especially in beta casein. For example, milk with A1, A1 or A2, A2 genotype show just one peak, while the A1, A2 genotype show two separate peaks. It even picks up on post-translational modification. For instance, a double peak in alpha S1 casein, which is likely due to phosphorylation, and multiple peak for kappa casein, probably because of glycosylation. So here we can see the chromatographic profile. Here show that each protein was meshed to known standard based on retention time, which made identification reliable. For consistency, retention time difference were really small, less than 0.47%, and the peak area variation was also low, both within a single day and across different days. So we can conclude that this method showed really good repeatability and reproducibility. Next is quantification of milk protein. Now on the quantification part, the method shows strong linearity whereby R squared is more than 0.992, meaning that the results stay accurate even with different sample volumes, and the recovery rate were very high, almost all around 100%, which shows excellent accuracy. Plus it was sensitive enough to detect even small amount of protein. Then this method also was tested on different milk types, which is raw, pasteurized, and ESL milk, and the result matched up with values from previous studies. There was also small differences in protein level between raw and heat-treated milk, which makes sense due to their processing effect.
For the conclusion, this study demonstrates that RP-HPLC is a powerful, rapid, and reliable technique for the simultaneous separation and quantification of bovine milk protein fraction and their genetic variants. It highlights HPLC's vital role in protein analysis, offering high resolution, reproducibility, and minimal sample preparation, making it especially useful in dairy quality control and nutritional research. However, the method does have limitations. It may require further optimization to detect low abundant proteins, and its performance can be influenced by instrument calibration and sample complexity. Looking ahead, future research could focus on improving sensitivity and resolution, especially for minor variants or post-translational modification. There's also great potential in automating the process for high throughput applications, extending the method to other species, and integrating RP-HPLC with mass spectrometry for more detailed proteomic analysis.